So when we're talking about attractions, so officially what we're kind of looking at, and my screen is getting annoying, is that we can look at attractions as a spectrum. Okay, just like you could look at people with attractions as a spectrum between any two atoms. Okay? And we're picking very specifically any two atoms because we're trying to simplify it all the way down. So the attraction between any two atoms. You could look at those being very, very strong attractions between those atoms, and you could look at them being very, very weak attractions. Okay? And everything there in between. What we arbitrarily went through and did, much like the same thing we did when we talk about the colors of the rainbow. What colors are in the rainbow? Red, orange, yellow, green, blue, indigo, and violet. So there's not red, orange. That color doesn't exist in the rainbow. I don't have any red, orange. Maybe a little bit of red, yellow. How about maybe I don't know, what's yellow and green? Puce, is that puce? Okay, so those colors don't exist in the rainbow? Well, no, they do. Because those other colors represent different wavelengths of energy, and what we went through and did is said, well, I'm going to call this red, call this orange, call this yellow to create a clearer delineation for the individual colors within it. We're doing the same thing with our attractions, okay, and to varying levels. So the first pass that we take at this is that the attractions between those two atoms, we'll go through and say, well, the really, really weak ones are very clearly different than the really, really strong ones. Okay? And at some point, we're going to transition between those. Okay? So a strong attraction, I might call a bond. So that bond is now sharing of electrons. And if I look at the weak attraction, okay, well, it's not a bond. Okay? And naming something based off of its not is kind of a silly system. Okay? So that's where we come up with our term, our forces. Or what we use generally when people talk about forces is what we're talking about, not bonds. And that not bond is not sharing electrons. Okay? Again, we're using a not in our definition. It's a really awkward definition. But eventually what happens, as we increase the strength from our not sharing electrons, eventually what starts to happen? We start to share electrons. Right? That's going to happen somewhere in that spectrum. And so what we went through and did is said, well, I think that happens here, at that magical point, okay, which means everything in this range is going to be defined as a bond. And everything in this range is going to be defined as forces. Okay, so we can just leave it as that, as two categories. Okay, so the rainbow, if we took red, orange, yellow, we put it all together, I'm going to define those as orange. So the rainbow is orange and blue. That's all a rainbow has in it. Well, no, it has those other colors. You're right, it does. So what we did is we further refined each of those categories of our bonds and forces. We further looked at it and said, well, if I looked at a strong bond that's on the very extreme end of that spectrum versus a different bond at the other end of that spectrum, well, they have different properties. Since they have different properties, I want to create a category that defines them separately. Okay? The categories when we're looking at our bonds is we could refer one category as a covalent bond and that other category as an ionic bond. Right? In the covalent bond, we get equal sharing of electrons. In the ionic bond, it's unequal, and depending on how far you want to push it, it's fully not sharing electrons. But now we run into this gray area. Are we not sharing as a force, or are we not sharing as a bond? Right? And so anything on that line that's delineating those is now going to be challenging to nuance and ultimately define. Okay? So we've got those categories. Well then, but what if I had, and attraction somewhere in between. Well, that's not really a strong bond anymore. That's also, or not really a covalent bond, because it's not an equal sharing of electrons. And it's not really an ionic bond, where it's unequal sharing of electrons. It's something kind of in between. Right? And that's where we would go through and say, well, we have a polar covalent bond. You always say, well, how do I know which one's which? Okay, well, there's multiple ways to come up with it, and ultimately it's all coming back to our atoms' ability to share electrons with each other. Right, well, that sharing of electrons is best monitored or quantified when we look at electronegativity. So we could go through and look at the difference in electronegativity between the atoms, okay, in our quote-unquote bond, and define that difference based on either being covalent, polar covalent, or ionic. So for the ionic bond, we define that difference to be larger than 1.7. Okay, honestly, I don't remember. Okay, and that becomes the challenge. This is supposed to be an accepted definition. Does everybody follow accepted definitions? No. Okay, so you'll get some variability within that choice. Okay, the polar covalent bond becomes a challenging one because it's a difference that's less than the ionic but greater than the covalent. Okay, so well, the covalent is going to be a difference in electronegativity that's less than 0.5. Okay, why did we pick those numbers? Because more or less that appears to be where we're seeing a difference in the chemical properties of that bond. So we're creating a human boundary on this system that helps us to classify and predict some of the chemistry. Does that mean it always works? No. But it helps to model the chemistry more often than not. So we create those systems. The problem with defining things based off of electronegativity is if I asked you for the electronegativity of oxygen, you would tell me it is silence. Okay, that's a bit of a problem. Okay, so you don't know the electronegativity? Are you like, oh, it's on the periodic table? It's not on the periodic table. Someone had to go through and quantify, calculate it, and put it in its own little table. Right, which would mean you would have to interpret a whole nother system or memorize a whole bunch of extra numbers. That's absurd. Okay? And you might think most of this course is absurd, but that is legitimately absurd. Okay? Nobody has the electronegativities memorized. Maybe somebody does, but let's just say nobody. Okay? I don't know them. And I work with these elements all the time. Okay? So it doesn't make sense to have a definition that gives us this information if we can't use that definition. That's where we create rules of thumb. Okay? A slightly different version that we can use categories that we should already know. So for instance, our ionic bonds we know as being ionic because we see metal and a nonmetal. And if we look at our electronegativity trends, all of our most electronegative elements are in the upper right-hand corner. You mean all the nonmetals? Yes. And all the lower electronegativity elements are all towards the left. You mean the metals? Yes. So if we put a metal and a nonmetal together, we're getting a large difference in electronegativity. That makes sense to call those our ionic systems. Okay? When we look to the covalent bond, this is supposed to be equal sharing of electrons. Okay, so we said less than 0.5. Okay, officially, it's absolute 100% equal sharing of electrons, and that only happens when you get the exact same element bonded to the exact same element. Okay, that definition is too narrow because there's other bonds that act like nonpolar bonds. So what we had to do is expand our definition a little bit, and our rule of thumb boils down to two things. I typically say same to same. And then the second one is carbon to hydrogen. Okay, why would we pick carbon to hydrogen as the extra one to add to this? Where do you see carbon? It's in your hands. It's in your eyes. It's in your hair. Carbon is everywhere. It's part of our biological system. Carbon makes up life. It's organic chemistry. So carbon is so prevalent that having a definition that centers around carbon is pretty useful. So we could look at the bond classifications and the chemistries associated with all of the carbon bonds. That would be organic chemistry. And from that class, we come back and say, you know what? The carbon to hydrogen bond doesn't really do anything. It's a pretty useless bond. Okay, why is it useless? Because it doesn't interact with anything. Why does it not interact with anything? Because it's not charged. It has a neutral charge. Why is it neutral? Equal sharing of electrons. So we define effectively our covalent category, what I call covalent, to be same to same and carbon to hydrogen. There's plenty of other elements that, or bonds that saddle into that system, but those require looking at the raw definition, which is electronegativity. Okay? So this then sets us up with polar covalent. What's going to be our rule of thumb for our polar covalent? Very similar to how we defined it to begin with. It was whatever was left over. So if you know what an ionic bond is, you know that. If you know what a covalent bond is, you know that. Anything that didn't fit those two categories is by definition polar covalent, which is why in the lectures we call that everything else. Okay? We can come up with different ranking systems within those and evaluate based off of knowing more information about our electronegativities. Okay? But we don't have to do that. Okay? This gets us to a baseline of functionality that allows us to make lots of really wicked predictions pretty quickly. So that falls now as our bond types. Okay? The other side of our line was the weak attractions. Those weak attractions could similarly be divided up. And when they get similarly divided up, what we encounter is the weakest interaction was so weak that we said it was non-existent. So we didn't name it until some smart ass came along and was like, nope, actually it's important. You do need to name it because we have to talk about it because it controls how gases work. That's kind of a big deal. Okay? So that super, super weak attraction, we would define as what? Anybody remember? It's cool. London dispersion force. Okay? Or would I write LDF? Because I don't want to have to write out London dispersion every time. Okay? That's now an incredibly weak attraction. Okay? And if we push to the other end of our ionic attractions, the other end of our attractions, we're now becoming stronger. We could look at that red category. That red category comes real darn close to be acting like a bond. Okay? What bond is it becoming like? An ionic bond. So one of the first passes that we used to name or classify this would have been calling it ionic. That should immediately be a problem, and whoever came up with these names should have seen this and been like, that's a stupid naming system, because I don't want to name an ionic bond versus an ionic force. Because ultimately we're going to get lazy and we're just going to call it ionic. Well, what the hell are you talking about? Are you talking about the bond or the force? Because those are different things. They mean different things. They have different applications. So they should have immediately been like, we need a different name for it. Right? That didn't happen. I think it's more recent that we came about and we started calling it electrostatic.
Yeah.
I think I did spell that right. An electrostatic force. Okay? Do people still call the force ionic? Yes. Why? They've been trained, okay, for probably hundreds of years to call the force ionic, not electrostatic. Okay? That becomes a problem for students because now you're in the system of if someone says ionic, are they talking about the bond or the force? You genuinely don't know. So that's where you should press as a student and be like, what are you talking about? Okay? Stop using that old-fangled technology names and tell me what you actually mean. Okay? And if that happens enough, maybe those old people will actually realize that they're screwing up the education system and we need to fix it. Okay? Except, how many times do you point out your instructor's failures? Ooh, interesting. We get silence again. Okay? So you have to contribute to that to help change that system. Okay? And you may say, well, it's not a system I have to worry about. I finish this class and I'm done. That's what everybody else has said, which is why you're now having to deal with it. Okay? So the more you can press the people that are trying to use those terms and tell them, hey, you're using a nonsense term, be better, the faster this changes. Ultimately, I would bet what we're going to wait for is a very long time, because what we're waiting for is all the people that use the term interchangeably, ionic bonds and forces, we're waiting for them to die, as morbid as that sounds. Okay? And I think I've made this analogy before. We're waiting for old people to die so that we can move on. Okay? I'm in this category this time, because I use ionic interchangeably. Okay? Theoretically, we've got a long time for that. Okay? There's still people younger than me that still use these terms interchangeably. Okay? So we have to wait for multi-generational systems to actually fix that naming system. It's very confusing, and unfortunately, you just have to deal with it. Kind of, sort of? Cool. We also continue to go through and look at this, and we define or note that we'll get that similar green area, that space in between. That attraction we deem or name a dipole-dipole.
So do we decide electrostatic is ionic force and ionic bond is the strong one?
Electrostatic, by definition, is a force. The ionic is, by
Definition of bond.
unfortunately, not defined, okay, but should be defined more clearly as a bond. Okay? And it's going to get further muddied in a second, unfortunately. Okay? Does that kind of make sense so far? So these are our big sweeping systems. We've got this band of all the possible attractions. We've divvied it up into different categories. And now we would then have to manipulate and understand and use those systems in varying ways. You'll note that I've colored things in very particular colors. Okay? I don't always do colors well, but this time I think I did a half-decent job. When we look at the covalent bond, that is such a strong bond, does it want to interact with any other element or any other bonds? No. If I have atom A and B bonded covalently, they don't want to talk to anybody else. So their interaction with any other atom is negligible. It's effectively zero. That sounds an awful lot like a very weak force. That's because it is. Okay? The covalent bond generates weak London dispersion forces. Okay? That's a natural repercussion. Okay? So our force is looking at a secondary interaction. The bond starts our conversation off, and then the force is what happens when we bring in something else. If I look at an ionic bond is a very weak attraction on the bonding side. It's so weak that what does it need to do? Find other things to stabilize it. And so in reaching out to find those other things, it's now making contact with something else. That something else is now a stronger interaction. So if I understand the types of bonds and what those things mean, I can now start to predict how those things are going to interact out to another molecule. So this green part we could call our forces in my little diagram, and this red part is what we'd be calling our bonds. But our focus point starts on what's happening within the bond. We then can apply that to a new interaction looking at a force. Okay? Within this system, I noted that the covalent is now tied to the London dispersion. The covalent bond, this very strong bond, is tied to a very, very weak force. But those are on opposite ends. Okay? That makes a whole lot of sense, okay, within that system. But then if I'm trying to remember how a bond is tied to a force, that can be kind of challenging. So what did I do within the videos? Take that bar of strength of forces and curl it. So now that when I look at a covalent bond, curled down, I guess technically that's over here, curled downwards, that's now going to be close to the London dispersion force. Okay? So you can look kind of laterally across the system to see what bond is generating what force. Kind of, sort of. Okay? So the image that's in the slides is really missing this bar, because it should start with that bar and say this is how we're dividing it. We then bend that to generate that system. Okay? With that bent system, we can now evaluate sorts of strengths of interactions and all sorts of other things and the ties between it. So there's a lot of information that then falls out of that diagram once you understand the individual pieces behind it. Kind of, sort of? Okay. So when we talk about our bonds, there are 3 bonds you need to be aware of. We have ionic, we have polar covalent, and we have what I call covalent. Okay? The covalent category, you will typically see people add an extra word to it, and we'll see non-polar covalent added to that. Okay? I would argue that's redundant. Once I've defined polar covalent, what's the other one? Not polar covalent. You mean non-polar? Yes. Okay, so I don't need to add that language. Okay? When it comes to the forces, every force is going to have a corresponding bond. Right? Because that's what's happening. You're looking at how that bond interacts with the rest of the world. So if I have a non-polar covalent bond, that's going to generate a London dispersion force, color coding. A polar covalent bond is going to generate a dipole-dipole force. An ionic bond will generate an electrostatic force. Those things are tied across that system. I'll try it again. Let's see if I can pull it off. The non-polar covalent bond is tied to our London dispersion forces. The polar covalent force is tied to our dipole-dipole force. And our ionic bond is tied to the electrostatic force. Okay? This becomes powerful because when we go through and look at structures, remember how we did Lewis structures? If we look at our Lewis structures, we typically look at a single molecule. There's lots of bonds within it. Each of those bonds can have an interaction with its environment. So we could start to evaluate how that bond interacts with its environment. Because we can see the bond, and since we know how they're tied to the forces, we can start to predict, is that going to be a strong interaction or a weak interaction? Kind of, sort of? Okay. The next part that we would layer into this is that if we talk to, most people, when they go through and talk about forces, they don't define electrostatic dipole-dipole and London dispersion. There's usually a couple changes that come into play. Number one, the London dispersion has a really wacky name behind it. Electrostatic and dipole-dipole come directly from the bonds that make them. So if you evaluate what's happening in the bond, electrostatic as a name and dipole-dipole as a name makes sense. I can't look at the non-polar covalent bond and say London dispersion makes any sense. What the hell does the capital of England have to do with anything? Okay? That's ultimately because it doesn't, and I don't remember the history behind that. Okay? It might be because the person that defined it was in London. I genuinely don't know. Okay? That seems like a really silly way to define a name, but hey, that's the way it is. So other people are like, that's a dumb way to name it. You should name it after the person that discovered it. So you'll hear van der Waals forces. Right? Which is why I suspect they weren't in London, because van der Waals doesn't sound British. That sounds German, or I was going to go Dutch. I was actually going to say Netherlandish, but I'm pretty sure that's not a thing. okay? Even then, you'll get other people, okay? Arguably me, okay, that goes through and says, I don't care who discovered it, give me a name that actually makes sense to what it's doing, okay? So you'll hear another name that comes across, which is very precise to what it's actually doing, and that's induced dipole, induced dipole. And that wasn't a stutter, that's, you have to say both parts of that. It's induced dipole and induced dipole force, both of those things, okay? That makes a lot of sense from where it's coming from, okay? But that's a giant mouthful, which is why I never bother to use it, okay? So you get all sorts of different issues with coming up with names, right? Okay, so you'll see that potentially come up with our London dispersion force. Ultimately, they're all weak. The other thing that'll pop up is you will also hear of another force. And because generally speaking, nobody takes chemistry first the way they should, they take biology instead, because biology is easier, even though they spend the first 6 weeks trying to teach you chemistry miserably. I'm happy that's recorded, and I'm glad to have any biologist come yell at me. Okay, I don't teach biology, get the frick out of my class. Okay? You'll go through and say, well, what's the other force? Right? We didn't get anybody shouting it out, but it at least was mouthed out. You'll see, whoops, I started to go into the abbreviation right away. Hydrogen bonding, which immediately should set up all sorts of alarm bells. It says hydrogen bonding, and where am I writing it? I'm writing it on the force side of the category. Why? Because it's a motherfucking force. Knock it off, you dumbass biologists. Okay? It is not a bond. Okay? It is a force. Okay? Why do they want to call it a bond? I actually am against that. I think they do actually know better. There's a good reason for why they want to call it a bond. It is such a strong, attractive force that what they're trying to do is emphasize the fact that it is so strong, it mimics becoming a bond. That's a really strong thing. Like, that makes a lot of sense. It also includes a whole hell of a lot of confusion behind that system. Okay? Which is why I would argue they end up calling it a bond anyways, because they're confused about the meaning. They're like, oh, it says bond, so it must be a bond. No, it's not. It's a force. Okay? And let's add a little bit of insult to injury. Let's rain crap on chemists too. Where is hydrogen bonding showing up in your textbook? Anybody know? Because you all been reading the textbook, right? Yeah. Well, what chapter did hydrogen bonding show up? Showed up in chapter 12. Chapter 12 is all about Lewis structure, which is all about bonds. The textbook editors have thought the hydrogen bonding force was so important that they decided to add even more confusion to the matter by including hydrogen bonding in the bond chapter. It's not a bond. It shouldn't be there. Okay? So, very strong attractive force becomes very important to manipulate. We need to recognize that. Okay? Which then starts to layer in some of the next kind of pieces that could kind of go through and deal with this. I went through and color-coded, not according to the bending of the rainbow aspect that we were talking about within the slides. I went through and color-coordinated because of how I arbitrarily started writing these things down, and I started talking about nonpolar covalent first, so of course I started with it at the top. Okay? If we were actually going to look at the strength of these attractions, which bond is the strongest? Which bond is the strongest? It's covalent. Remember? What we're asking about is right there. Which bond is the strongest? The covalent bond is the strongest, by definition. Which force is the strongest?
Electrostatic.
Our electrostatic, or as we started to mouth out with the added confusion, ionic. Okay? Yeah, we should be calling that the electrostatic force is the strongest. And you might be like, well, if you added arrows, we're saying stronger over here, but now we're saying stronger over here. Aren't they opposites? Again, they aren't technically opposites when you consider where they're coming from. They're opposites in how I've drawn it out because I drew it out stupidly. Okay? So we have to be careful in recognizing those patterns. The stronger the bond, the weaker the force is going to be. Because if it's a strong bond, there's no need to look elsewhere. Okay? If there's a couple that get along really, 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 really well, what's the infidelity rate? Next to nothing. Because they get along really, really, really well. That's a strong bond. But if you get a couple that is constantly fighting with each other, what are they going to immediately try and do? Reach out to find somebody to help them out. Okay? That strong attraction in between isn't so strong because they're constantly fighting with each other. So they need to find somebody else to help them through that system. And depending on who that somebody else is, that could ruin that relationship, okay? Or it could make it stronger, depending on those systems. Okay? In chemistry, that there is no making it stronger. And it's just like, if you're reaching out, you're done. That bond's gone. Okay? But relationships, that can change. But it's a similar idea. Kind of make sense? Okay? So why do we care about classifying bonds and forces? You should have asked that at the beginning of the semester, Mike. I haven't cared about anything you said. Thanks. I appreciate that. Makes me feel real good. Warm and fuzzy on the inside.
Do you predict how it's going to interact with outside forces or outside atoms?
We want to know how those molecules are going to interact with other things. Because if we can predict that, we can change that environment. We could change that environment to minimize a chemical reaction. Oh, I wouldn't want to do that. Yeah, we do. Uranium, I want to minimize that bond interaction causing an explosion. That's a bad idea. I want to minimize that. Okay? There's other systems where I want to maximize an interaction. Why? Because I'm trying to make something new. So I have to understand something about those attractions between those individual atoms to be able to come up with predictions. The typical predictions that you're responsible for aren't big, complex ones like dealing with uranium or anything else. Okay? What you're primarily concerned about is the physical properties. Okay? Physical properties like melting point, boiling point, okay? Solubility. Those physical properties are the ones that you're trying to predict. And here's where we encounter one of the next big confusions. Right? If I take a look at salt, right? Salt. What is salt? NaCl. What kind of bond is that? Ionic. Right? And I want to predict something about, I don't know, its melting point. What do I have to do to melt it? I have to break all the intermolecular forces around it. Okay? And if I go through and look at all those intermolecular forces, what are the intermolecular forces in salt? Well, if it was an ionic bond, what are the forces? Metal, nonmetal is ionic. What's the force? If I have an ionic bond, I have the electrostatic force. Okay? So hold that, because we're going to come back to that in a second. Now let's take a look at, let's pick water. What's our structure for water? H2O. Okay, cool. Or our formula for water, H2O. What kind of bonds do we have in water? We have our polar covalent bonds. It's not carbon to hydrogen, it's not same to same, and I don't have any metals. Okay? So the polar covalent bond, is that stronger or weaker than the ionic bond? It's stronger. So if I went through to melt water versus salt, what would I predict? And I have intentionally led you astray, for the record. Why?
Because it has a stronger force.
Okay, so you've shifted this. Okay, you actually took it to the next step beyond this. When I went through and said it, our water has what kind of bond? Polar covalent. Our salt has an ionic bond. Which one has the stronger bond? Polar covalent is stronger. And if I have a stronger bond, shouldn't it require more energy to cause it to change phases? You would think. Except, what's the phase change controlled by? Not the bonds, the forces. And so when I go through and look at a polar covalent bond, it's generating which force? Dipole-dipole. When I look at the salt, I'm looking at an ionic bond, which generates which force? Electrostatic. Which force is stronger, electrostatic or dipole-dipole? Electrostatic, which is why salt has a higher melting point than water, because it has much stronger attractive forces within it. And what I'll hear people saying is oh, that means ionic is a stronger bond. No. The physical property is controlled by the force, not the bond. We look at the structures to determine the bond so that we can then correlate that to the forces. Now we can interpret our physical properties based off of the forces. The covalent bond is stronger than a polar covalent bond, is stronger than ionic and fudge. Too many vowels. Then the last one, the red one. Okay? But all of our physical properties come from the forces. Which means when you go to a test, what are you going to see? You're going to see a single structure. You're going to see a molecule. That molecule will allow you to interpret the bonds. But the question will ask about the forces. The forces is how those bonds interact with other molecules of the same type. So what you have to do is evaluate the bonds, convert that into forces, now do your interpretation for whatever the question is asking. Okay, which is misleading, because you would think, well, if the forces were important, why aren't you drawing out the forces for all of my structures so I could evaluate those? Why not? Can I delete everything? If I want to talk about the forces that this molecule exerts on another molecule, what do I have to do for an answer choice? I have to draw a whole nother second one. Okay, and for those of you being like, well, that's not that big of a deal, did you write it out? Yeah, I didn't think so. Okay, it takes, and we ask you to use your imagination. Why not? Imagination to answer the question about the forces. How imaginative are you? That's personal to you. Okay? If you're not very imaginative, then what do you think you should do? Draw it out. Okay? If you're imaginative, then cool. You don't need to draw it out. Do it in your head. What was it? Be like Willy Wonka. Isn't that right? Isn't something about imagination? I think there's a song. I would sing it, but I don't know it. I think it says, in your imagination. Dang, I should have quit while I was ahead. The semester would never have started then. No? Okay, whatever. Are we good? Let's rein that back in. I think we got some baseline idea of what's going on within that now. Okay, which would then be, what do you want to look at? Should we look at a practice question on this? Yeah? Okay. So right away, this one becomes a little bit more complicated than what we've been looking at, because it's not just evaluating the individual bonds. We've actually got a couple different things going on within this. Okay, first and foremost, we are looking at names. There's names associated with these that causes people to panic and evaluate. We don't care. We're just giving you the name as random extra context, kind of like the quiz 3 or exam 3, with the first question giving you a whole bunch of densities. The name doesn't help you. Don't worry about it. What should you focus on? focus on the formula. The formula is also problematic in my opinion, but we've got ways that we can dodge that. And so we'll talk through this question by dodging it first, and then I can show you what it kind of means in a more appropriate sense. Okay, and you can see why we apply here. So we're talking about bonds and forces, so we need to be able to evaluate that for each of our individual structures. Okay, and we also have to be able to apply this to a new principle. Okay, we talked about using melting point or boiling point, our phase changes. We're not talking about melting point or boiling point here. What are we talking about? So we got a bunch of weird words coming in. So we got like dissolves like, and we have this miscibility. Miscibility is a fancy way of talking about, already stated, solubility. What is solubility? How easy a solute dissolves in a solvent. Okay? So for those people that were like, oh, it's how easy something dissolves in water. No, water just happens to be our most common solvent. We have to be a little bit more careful when we're going through with this question. If we're looking at solubility, we have to evaluate all the context that's given to us. Okay, but ultimately solubility, we've got a solute and a solvent. So we're looking at molecule A with some attractive force, or ultimately atom A with some attractive force to atom B in a separate molecule. So that's what we're concerned about. Okay, since I have two parts, I need to have two pieces. My answer choices provide me one of those pieces. The question has to provide me the other piece. So in reading through the question, what is one of those pieces? So like dissolves like is going to come into play in a second, but we're not even there yet. We're talking about solubility. It's A interacting with B. A is going to be one of our answer choices. B is going to be water. So what we're concerned about is how water interacts with our answer choice. Okay? Since we're talking about an interaction, before we look at the answer choices, what interaction would we expect coming from water? Well, what's our formula for water? H2O. And if we push on this really hard, really what we should be doing is actually drawing out a structure so that we could evaluate the structure. We technically don't have to. Okay, so don't stress about that yet. But if we look at water, what's the force that I'm going to be concerned about? Okay. To determine that force, the first thing I should be able to go through and do is evaluate the bonds that are present. The bond that is present in water is polar covalent. It's polar covalent because it's not carbon to hydrogen and it's not same to same. There's also no metal. I will admit the hydrogen placement on the periodic table is very misleading. If you remember all the way back at the beginning of the semester, we talked about its placement as well. But sometimes you'll see hydrogen placed right next to helium also. Right? And we typically float them off the periodic table because they don't really follow the classifications underneath. Hydrogen is a nonmetal despite its location. We have to remember that as a nonmetal. Okay? Because they're both nonmetals, we're not ionic, so we're not ionic, we're not covalent, which means we're left with polar covalent. If we have polar covalent, what kind of force comes out of that? Please follow directly what force comes out of it and not a secondary interpretation. That's going to be our dipole-dipole. Okay? And for people saying there's other answers, you're not wrong. We'll get to that. We'll cross that bridge in a second. Right? So, we've now at least gotten half of our problem figured out. We know what interaction water is going to produce. We don't know what interaction our answer choice is going to produce. Okay? But we're going to need some context to know what makes our answer choice a better choice. So that context has to come from the question. And there's really two places that it's going to come from. Number one, it says miscible. So miscible says that this substance actually mixes. So A does mix with B. Well, what controls whether A mixes with B? So we could try and do solubility rules, which we did when we talked about double replacement reactions. The problem with solubility rules is that those are talking about ionic compounds. There's not an ionic drop within this. Okay, so we can't fall to the solubility rules. And typically when we're talking about our forces, we're not talking about ionic compounds. Almost universally, what we're looking at is our nonpolar and our polar covalent structures, our molecules, not our formula units with our ionic compounds. Okay, so what else could we use to predict it? If not our solubility rules, well, what else do we know? How much of the lectures did you watch? If you've watched your most recent lectures, you now have an extra rule set that you should be following. Right? Technically, it's already defined within the question itself, but knowing how to apply it becomes the next part that you would have to worry about. Okay? That extra rule, when we're just talking about solubility, is that things will mix with each other when they have the same force. The more similar the forces, the more likely they mix. The more different the forces, the less likely they mix. This has to do with the strength of those attractions. You don't want to take something with really weak attractions and try and mix it with something with really strong attractions, because you have to break all of those strong attractions so that you can bring the weak thing in there. Well, no, to keep it strong. Okay, so the only way we get mixing is if the attractions between the two things are similar to each other. The attractions that we're talking about are forces. Okay? So the rule of thumb that comes out of this is like dissolves like. And what they're saying is like forces dissolve like forces. So to a first approximation, all we've got to do is find the forces. And if the forces are the same, ta-da, there's our answer, and we're done. Okay? So we could now start going through our answers. And actually, we don't even need to do that. What's most similar to a dipole-dipole force? It's really easy. What's most similar to a dipole-dipole force? A dipole-dipole force. So your answer choice needs to be something that has a dipole-dipole force. Like dissolves like. Like dipole-dipole dissolves like dipole-dipole. We've completed our statement. So now that we know what we're looking for, we can go back to our answer choices and try to define where we have a dipole-dipole force. And what we're going to encounter potentially right away, depending on how you look at this, is that you're given a formula. Can you draw the structure from that formula? Okay. And for those people saying confidently, yes, I can, 1, 2, 3, 4, 5. Okay, and now I fill all the rest of those in with I'm not drawing the hydrogens, but I'll show you the bonds. Okay, so cool, that's one. Is this the same structure or a different structure? It's a different structure. Does it have the same formula? Yes, it does. Ooh. Okay. What about 3? This one. Ooh, yes, it does. Well, dang. Which one is the proper structure? Did I count wrong? I had it right the first time. I just screwed it up and changed it. Okay? So which one of these structures is the one I'm actually talking about to determine my forces? Okay? And that's a hard question to answer. Okay? Ultimately, what do we care about? What are we looking for? I need the dipole-dipole force. Okay? So, what force do you see coming out of those molecules? Well, determine the force, what do you got to do? Look at the bonds. So what kind of bonds do we see in, we'll call it our red structure? what bonds are present? Carbon to carbon. What other bonds are present? Carbon to hydrogen. What other bonds are present? That's it. Okay? So we could go through and say, well, I have carbon to carbon and carbon to hydrogen. What kind of bonds are those? Those are nonpolar covalent. That's same to same. And carbon to hydrogen. Both of those are nonpolar covalent, which means the force that I get out of that structure is? Okay? And this is where tracking our forces becomes important. Those are nonpolar covalent bonds, which means they're very strong bonds. And because they're strong bonds, they're going to generate weak forces. Our weak force is London dispersion. So if we looked at that top structure, we would say it was a London dispersion force. What's our force when we look at the green structure? It's the same. It's London dispersion. How about the purple structure? It's the same. So was there a cheat that I could have looked at? Yes. Look at the formula, C5H12. What are the only possible types of bonds that you could put into that? C to C and C to H, which means regardless of where the atoms are actually located, the force coming out of that answer is a London dispersion force. Is London dispersion force what I wanted? Nope. So probably not that one. So the next one, what do I see? I see a bunch of carbons and hydrogens. The same thing I'm going to get, London dispersion force. Next one. Okay, so some people are saying same, and it's probably because they're not seeing the question super clear, so you got to be real careful with these. Okay? The difference here is that we're actually seeing a Cl. So we now process out that structure with a chlorine in it. I've got carbon, hydrogen, and chlorine. What kind of bond, at a minimum, am I going to get out of that? Nonpolar covalent, sure, there's a possibility, and polar covalent. Right? That polar covalent bond means I'm going to have what kind of force? A polar covalent bond does not generate a London dispersion force. It generates a middle, our dipole-dipole force. Okay, you say, oh, well, that must be the answer. Well, let's rein it in just a little bit. Let's move on to the next one. What do we see in the next one? Hopefully we see the presence of an oxygen. And what's special about the oxygen? Depending on what it's bonded to, it's right next to a hydrogen, which means we're looking at a polar covalent bond, which means dipole-dipole. We move to the last one. For some reason, they shuffled everything around, but ultimately all we see in there are carbons and hydrogens, which means what we're looking at is a London dispersion force. So we now have an interesting dilemma, because in our work, we said the similar force was dipole-dipole. We have two answers that make a dipole-dipole force. So how can we refine this? Well, to refine, we should go back and check our work. When we go back and check our work, yes, we have a dipole-dipole, but there's one really critical step that we should be adding, discussed in the videos, whenever you encounter a dipole-dipole force. Whenever you have a dipole-dipole force, what must you also check for? Does it have the potential for hydrogen bonding? Okay, so in the previous case, we just said, we had hydrogen bonding as a thing, but we didn't actually define it. So now we should define it. Right? What do you think needs to be present to have hydrogen bonding? Good guess, we need hydrogen. Okay? Ultimately, it is a dipole-dipole force. A dipole-dipole force means a large difference in electronegativity. Not super large, but large. Hydrogen, being to the extreme left of the periodic table, is going to have a relatively low electronegativity, which means this hydrogen is going to have to be connected to something with a high electronegativity. Well, carbon's on the far right of the table. Shouldn't carbon be enough? But it wasn't. Okay? So there's an extra piece of information we need to know. What electronegativity creates that threshold? Okay? And you're like, but I didn't memorize electronegativities. Fair. We need something else to define it. Have you had enough of my funny jokes? If not, we'll keep having some fun. Palm to the face was a pretty appropriate response. The elements that hydrogen must be bonded to are nitrogen, oxygen, or fluorine. Said left to right, enough of my jokes. Or if we flip it right to left, we've been having lots of fun. I'll be here all week, just like every other week. Okay. You can't try the veal because we don't have any. Okay, so when we go back and look at our water, do we have a hydrogen bonded to oxygen, nitrogen, or fluorine? Yes, we do, which means while I have a dipole-dipole force, I have to acknowledge that I also have hydrogen bonding. So if I'm now using this like dissolves like, yes, dipole-dipole is a target, but I also want to see hydrogen bonding. Right? So now what I should double back through and do is, do I also have the potential for hydrogen bonding? So this becomes an and statement. If I go back and look at my chloroform, I've got carbon, hydrogen, and chlorine. Yes, I've got the hydrogen, but do I have a hydrogen bonded to oxygen, nitrogen, or fluorine? Nope, which means no hydrogen bonding. Which might right away say that's now going to be a wrong answer. But again, we should jump to the next one and see what happens. Okay, I've actually highlighted it, which probably means it's not visible, but we can pull that out a little bit. It very clearly shows an OH. Do I have a hydrogen bonded to oxygen, nitrogen, or fluorine? Yeah. Yes, which means that molecule not only exhibits dipole-dipole, it also exhibits hydrogen bonding. So between answer choice, what is that, C and D, which one matches as close as possible water? D. Your answer is D. Kind of makes sense? Okay. Some extra things that we could throw out there because we talk through the whys and hows of how we solve a question. Okay. I wrote down a whole hell of a lot of stuff. Do you need to write that down? A couple different answers to this approach. Okay. Number one, okay, do you get credit for any of your work?
Yes.
It's all multiple choice. There is no show your work, so you don't have to write any work down. Okay? That can be both a good thing as a bad thing. Generally speaking, it's a bad thing. Your show your work scores on average are higher than your multiple choice. Okay? And I would argue one of the reasons for that is that when you're in a show your work, you're starting to write stuff down. And as soon as you write it down, it's now in a place where you can evaluate it and decide whether it was right or wrong. And if it was wrong, you can correct it. In the multiple choice, because you don't have to write things down, what do you end up doing? Not writing things down and doing it all in your head. Your head is a scary, freaky place to be, and it very commonly will screw you over. Let's just look at your relationships. Okay? Which is also, to me, I'm being fair, okay? World relationships. Okay? That's a problem. If you write the work down, you can track better your thought flow and you can ensure that you get to the answer correctly. Does that make sense? So while you don't need to show that, you've got to decide how much work is necessary for you to ensure that you get the correct answer. And if you can get it with showing no work, by all means, go for it as long as you're doing your own thought process work. Right? Copying off of somebody else is a bad idea. Make sense? All right. So within this, you got to decide how much work is necessary for you to solve the question. All right? That's up to you right now. Make sense? Sorry, I thought that was a question. Do we want to do more like this or move on to a different question? I don't know what no means. You're done? Yeah. I get it. For the sake of argument, okay, we will all be done Okay? You're going to get toast and feel burned out and just be done with it. You need to get used to that fatigue. And my rule of thumb, as soon as you feel that burnout, you got to do 5 more questions. Okay? Get used to that feeling so that when you hit 75 minutes in the exam, you still have another half an hour to go. Okay? That can help improve the odds of you actually being successful all the way through the whole thing. Okay. If you don't have questions, then what I will do is talk through something else. So we're going to go all the way back up to our table of contents. Do what I asked. We've got all these competencies written out, right? Each of those competencies lists the number of questions that show up in the actual exam, the actual final. What you should be able to go through and do is to read a question and decide whether that's one of these competencies or not. So what I would recommend you do is go through the exam, the practice exam, and for each question be like, that's this competency, that's this competency, that's this competency. Okay? Why? You know you have a question on every single one of those competencies. Does the practice exam actually have questions to give you practice on every single one of those competencies? Ooh. I don't think it does. Okay? Which means there could be gaps within that you aren't seeing unless you pay attention to the competencies that are all covered. Does that make sense? Okay? Even if it did cover them all, right? Some of this is going to come down to the amounts within each of those competencies. So it's asking for 3 questions on the number of protons, electrons, neutrons in any given isotope, neutral or charged. Okay? 3 questions on that. Maybe there's only 1 in the practice exam. If there's 3 questions on it, you should probably go out and find some more questions to review that content so you're better prepared for it. Okay? That can be done by mapping what stuff you have in front of you. Right? On top of mapping it, what I would also do is look at it and decide which competencies are you concerned about. Okay? Are you happy with your grade in the class right now? That's up to you to decide. And if you're not happy with it, part of all of those average, predict, all of those fun things was to help give you a number to try and target. So go through and look at these and be like, where should I spend my focus? Okay? I'm going to see 5, where did it go? 5 questions on naming and writing formulas. I suck at naming and writing formulas. Well, dang, find more practice on that. Improve that so that when it shows up in the final, you're better prepared for it. Just doing the practice exam may give you practice on 1 question, maybe 2. Right? You've got a textbook full of questions. Leverage that to your benefit. Right? You may also decide this most recent stuff with intermolecular forces. You're like, this is way too hard. I don't want to learn this. Okay, don't. Right? I can officially say I've taught it to you, but that doesn't mean you learned it. Right? So you could go through and entirely ignore that content and focus on the other stuff that is review for you to ensure that you up your percentage in those areas and you're sacrificing in other places. That's okay. I don't like it, but that's okay. That is a perfectly valid strategy to navigate the course. Make sense? Really nothing? Do you want 5 minutes apiece? Yeah? Too bad, you're in chemistry. Go for it. That's it.
Day and times are final.
I don't remember off the top of my head. I believe it is actually in Canvas. But what I'm going to do is show you some other way to do it. If you go to Google and type in CGCC final exam, or really final exam schedule, you'll see the final exam schedule, okay, and when is my final. So you can click this. It's going to open up a PDF. This process works for every semester because it gets constantly updated. So we are the Pecos campus, so we got to make sure we read everything. We meet Monday and Wednesday. Today's Wednesday? Yeah, okay, good. Class begins. Our class began at 11:30. So we're right here, Monday or Wednesday, 11:30. Our exam is gloriously... Go away. I never wanted you dictionary. Probably should use it more often. 11 to 12:50 on Monday, May 5th. Oof. Okay. So, couple things that are going to come out of that. Number one, when does our class start? 11:30. If you show up at 11:30, you've given up half an hour of your exam time. Okay? Because the exam starts at 11. Okay? So Monday, May 5th, 11 to 12:50. That's your exam window. So it's an hour and 50 minutes. Okay? Whereas your normal class is an hour and 15. So there's an extra, I do the math, 35 minutes, something like that you've got to deal with. The reason why I want to point this out to you, okay, because there's been lots of debate within this college and lots of people have gotten angry and pissed. Okay? So there's lots of name calling. Go figure, right? I'm at this college. The reason this schedule exists is to minimize conflicts between final exams. That's why it exists. So if your instructor is not following this schedule, they should be reported. Full stop. They need to be reported and they need to be told, this is the schedule. You cannot expect students to meet outside of this schedule. Okay? There are a few cases that you run into issues. For instance, time of exam, arranged. So if you had a class Monday, Wednesday, sorry for you, starting between 7 and 7:25, which really means I think just starting at 7, that instructor can make their exam whenever they want. Okay? There are some limitations within that. Like you can be like, I can't make that time because I'm in another final that follows the schedule. You need to provide another time. And they need to listen to you. That's how it works. Okay? If they aren't listening to you, you need to find someone with more power to make them listen. Okay? That can be me, but usually what I'll do is just forward that on to someone with actually more power, okay, to get that clarified. Kind of, sort of. This will work for the rest of your classes, the rest of your time at Chandler Gilbert. So Google CGCC, finals, final exam schedule. It'll be posted. Check it out. Make sure your courses are following what the schedule is supposed to be. So there you go. Sorry, I ruined your piece. But I'll stop now.